SwayamPrabha. Digital India. Educated India.
Welcome back. In this video, we'll continue upon this classical laminate theory that we have been discussing in the previous video. So in previous video, we have looked at the two steps involved in the classical laminate theory. Meaning, first we started with what is the relation between the stress and strain for the kth layer. That we have shown in the body coordinates x and y using this transformed stiffness matrix Q dash. In the second step, using deformation hypothesis, we have shown what is the relation between the stress and strain in the laminate. Essentially, we made few assumptions regarding the deformation, saying that the normal should remain straight before and after deformation. This is the normal to the mid surface of the laminate. So it should remain straight before and after deformation, and we said it should remain perpendicular to the mid surface both before and after deformation, and lastly it should be of the same length before and after deformation. Using these three hypotheses, we were able to show what is the relation between the strain and the displacement, and finally between the relation between the stress and strain. So in this video, we will be focusing on the last step, where we now start to discuss about what are the forces and moments applied on this laminate. We will write these in terms of the strains and curvatures which we have shown here. So these are the mid-plane strains and these are the curvatures. So we will try to write these forces and moment in terms of the strains and curvatures. So let's consider a laminate, a planar laminate, where it is in this direction of x and y. So it is on the xy plane, and we previously mentioned that z direction going downwards is positive. So here is the z axis which is going downwards. Now let's focus on the forces which are applied in plane. So on this face there is a horizontal force Nx and a shear force Nxy. Similarly, on this plane, we have the normal force Ny and the shear force applied Nxy. And the same forces will also be applied in the opposite plane, which is behind. Similarly, these forces Nx and Nxy will be applied on the opposite face, which is shown here. Okay. Now let's see how can we write these forces in terms of stresses. So starting with Nx, we can write it as anytime force is stress times the cross section area. In this case, we'll take the thickness dz going from minus t by 2 to t by 2. So we are considering this thickness t, and for the width we will consider it as unit. So essentially this Nx is per unit width, because we are assuming that this is 1 and this dz times 1 is the actual cross section area on which these stresses sigma x's are applied, and because of these stresses we get to this normal force Nx. So we'll look into the other components in the next slide, but similar to forces we will have another definition for movement. So here is again the same laminate. The only difference is, instead of showing the forces, now we are showing the moments. So on this plane, we show the moment mx and mxy. So the moment mx is coming from the stresses sigma x, and the definition is here. So the moment is given as stress times the distance from the mid surface. So let's say this is the mid surface. So any point, if we take how far it is from the mid surface is represented by this value z, that times the stress gives you the moment times the cross section area will give you the moment. And here too we are taking dz times 1, where 1 is the unit width, So this is the moment per unit width. So the similar definitions we can also apply for the other components of moments, which are mx, my and mxy. So essentially moment mx is coming from the stresses sigma x. Similarly, moment my will come from the stresses sigma y, and lastly the moment xy will come from the shear stresses sigma xy. Okay. But before we go and derive what is the relation between these forces and moments with the stresses and strains, let's also be clear about the notations where we define the Z for each lamina. So let's say here is the cross section of a lamina we are considering. And as we mentioned previously, we start from the top layer. So one is the top layer and then keep going downwards in the sequential pattern. So the second layer, the kth layer and the nth layer. But now the question is, how do we define the Z values in each of these layers? So we start with the mid surface. Let's say this is the mid surface, where we say the Z value is 0, which means the this axis passes through the mid surface. And we also mentioned that the Z direction is going downwards for positive. So the Z goes downwards for positive, which means we know that the total thickness of the laminate is T, and so we have T by 2 in the top half and T by 2 in the bottom half. So now let's see how we can start notation. So Z naught will be the top surface, and what is the value of Z naught? It is a distance of T by 2 from the mid surface and in the negative Z direction. So we should write it as minus T by 2. How about Z1? So now let's move to Z1, which is basically the bottom of the first layer. So for that it will be minus T by 2 plus, let's say, H is the thickness of each layer. So for now let's assume that all layers are of equal height H. But of course this is not true all the time. We can have definitely lamina with different thicknesses in a laminate. Now similarly Z2 will be minus T by 2 plus 2H and so on and so forth. And similarly for the kth layer, we can write ZK minus 1. So in this fashion we should be able to write this bottom of this laminate. This will be Zn equals to T by 2. Now it is a positive value because we are in the positive direction of Z. Okay. So this should summarize what is the definitions of the forces and movements we are taking, and what are the notations we are using to give these values of Z for each layer in this laminate. For each layer in this laminate. Now let's focus on forces. So here we are reproducing the same laminate and we have shown these forces Nx, Ny and Nxy. So again previously we have already shown you what is the definition of this Nx, which is written in terms of the stresses sigma x. Now let's see how we can write this force Ny. Ny will be integral of, this is coming from the stresses sigma y times dz, and these integrals go from minus T by 2 to T by 2. Essentially it goes from top layer to the bottom layer. And similarly Nxy can now be written as in terms of the stresses sigma xy or tau xy times dg, going from minus T by 2 to T by 2. So let's write it in terms of tau instead of sigma. Okay. Now we have the definitions for nx, ny and nxy. What we'll now do is we'll collate all these three equations into a vector. So we'll now write a vector for these forces, which consist of these nx, ny, nxy. We'll bring it into a vector. Then I can write it these three equations combinedly into one single integral. So all these three integrals have the limits from minus t by 2 to t by 2, and this vector captures the stresses sigma x, sigma y and tau xy times dj. Okay, now let's see how we can introduce the number of layers. So here, instead of going from minus t by 2 to t by 2, I can write it as a summation of number of layers, and in each layer individually I'll write this integral. So this summation should take care of number of layers going from 1 to n, and in each layer we again apply this integral, but this time instead of writing in terms of t by 2, we'll write it in terms of z, because as we have just shown, for each layer the top layer will be zk minus 1 and the bottom of the same layer will be zk. Now for these stresses in the kth layer, previously we have shown how to write it. So stresses in the kth layer we said is written in terms of the stiffness matrix or the transform stiffness matrix times the strains times the strains. So how do we write the strains? We wrote it in terms of the mid surface strains plus z times the curvatures. Okay. So now once we substitute this in place of the stresses in these equations here, now what happens? Now let's focus on this Q matrix. This Q matrix will change from layer to layer, meaning it is a function of the layer. But whereas these strains, the mid-surface strains and the curvatures, these always remain the same irrespective of the layers, because these are written for the mid-surface. So once we see that these stresses can be written in terms of the mid-surface strains and the curvatures, we substitute that in this equation here. So, and once we substitute, we need to make few observations. First, this Q, which is the stiffness matrix, this changes from layer to layer, but it is a constant within a layer, meaning if I am bringing it back here, where can I pull it? Can I take it out of the integration? The answer is yes, because this integration is with respect to dz, but the stiffness matrix within a layer, it's not a function of z. So we can take it out of the integration, but we cannot take it out of the summation because for each layer these q values are different. Okay, but there is one other thing we can do. When we consider these mid-surface strains, we know this doesn't change with layer to layer, meaning they can be taken out of the summation, but they should still remain in the integral. The reason being, integral is with respect to dz, and these values of strain plus z times k, right? So this expression should be in the integral. So now let's see, these q's we can take out of the integration, and these strains we can take out of the summation. We write it in this fashion. So we now write these forces as summation of Q matrix. If you now see this Q matrix, we have taken out of the integral because it's not a function of Z. But we have kept it within the summation because for each layer these Q values change. But when it comes to the mid-surface strains and the curvatures, we know we need to still keep them in the integration because these are functions of Z. At least this z times curvature is a function of z, so we should still keep them in the integral. But it can be taken out of the summations because from each layer they don't change. They are constant across the layers. Now let's see how we can simplify them. So now finally we write these forces in terms of a new matrix called A. We will just define what is this matrix A. times the mid surface strains plus the B matrix times the curvatures. So in a moment we will see what are these matrices A and B, but the whole idea is we are now able to write these forces in terms of the mid surface strains plus the curvatures. Now the question is to see what are these matrices A and B. So if you look closely, actually we should be able to write those. So this matrix A is nothing but the product of the stiffness matrix component terms times the zk minus zk minus 1. What is this value? This is simply the thickness of the layer. And for the B matrix, we have the stiffness component term times the z square by 2. And where are these coming from? So if you look here, it is simply integral dz. And the second term is integral z times dz. Because the mid surface strains and the curvatures can be taken out of the integral, let's say these are the mid surface strains and these are the curvatures which are taken out of the integral. And now once we apply integral of dz is simply if this is going from zk minus 1 to zk, we should be writing this as epsilon times zk minus 1. That's exactly what we have written for the A matrix. We are talking about these terms for the A matrix, and for the B matrix, since we have an integral z times dz, it should be the curvatures k times z square by 2 evaluated in the integrals of zk minus 1 to zk. And once you evaluate that, this should give us the B matrix terms. So here we have this zk square minus zk minus 1 square, and this half is coming from the integral. And where are these stiffness components coming from? These are coming from this stiffness matrix, which are changing from each layer. That is why we need to write it in terms of k is equal to 1 to n, where n is the number of layers. So this should summarize basically the relation between the forces written in terms of the mid surface strains and the curvatures. The similar derivations we can now show for the moments as well. So here is the depiction of these moments mx, my and mxy. Mx we said is written in terms of the stresses sigma x times z dz. Since this is a moment with respect to width, we are taking that it's a unit width, otherwise it would be times 1. Okay. And similarly my, we can follow the same expression, the only difference is this will be sigma y times z dz, going from minus t by 2 to t by 2. And mxy can be written as tau xy times z dz, going from minus t by 2 to t by 2. Now we have these three equations to show the three components of the moments. We can, similar to the forces, we can bring them to one vector. So this is the vector representing or collecting all the moments, and this is the single integral to capture these three equations, where we have this vector having the components of stresses times z dz. And since in the first integral is written in terms of the laminate going from top to the bottom, now we are writing it in terms of each layer. That's why we got the summation k minus 1 to k going from 1 to n, and each layer going from k minus, and for each layer we write it integral in terms of zk minus 1 to k in terms of the stresses and z dz. So once we have it, now we will again recall that stresses is written in terms of the transform stiffness matrix q bar times the mid surface strains epsilon naught plus z times the curvature vector. So once I plug in here, and make the same observations we made in the previous slide, saying that the stiffness matrix is constant within a layer but changes for each layer, whereas these mid-surface strains and curvatures are not a function of z. So then we can make some simplifications. So where we got this Q matrix out of the integrals, and these integrals will be only for the z dz and z squared dz. Okay. This can be further simplified, and now we can write these moments in terms of the B matrix times the mid surface strain plus the D matrix times the curvature. And this B matrix is repeating from the previous slide, where we showed that B matrix is written in terms of components of the stiffness matrix times Z terms, Z square terms. The only difference with D matrix is, here since we have Z square in the integral, so this integral Z square dz will be Z cube by 3 going from Zk minus 1 to Zk, which will be this Zk cube minus Zk minus 1 cube by 3. So this explains the 3 here and the cubic terms for Z values here. So in summary, let's see what we have learned till now about the forces and the moments. So for the forces, we said we are writing in terms of the matrix A and B. For the moments, we are writing in terms of these matrices B and D. So these are the commonly termed A, B, D matrices. And each one has a terminology. We call this matrix A as the extensional stiffness, because what does the A matrix do? It connects the forces with the strains. B matrix, we call it as the bending extension stiffness matrix. The reason is because it connects the bending to the extension. Looking at the first equation, what does the B matrix do? It connects the forces N to the curvatures. So the curvatures take care of the bending, and the extensions are taken care by these forces Nx, Ny, Nxy. So this B matrix is connecting the forces with the curvatures in the first equation. In the second equation, it is connecting the moments, which captures the bending, to the extensions, which are captured through the strains, mid-surface strains. And lastly, the D matrix is the bending stiffness matrix, because it connects the moments with the curvatures. So as you can see, D connects the moments with the curvatures. So each of these matrices A, B, and D has a physical interpretation. Usually for isotropic materials, we don't have this bending extension stiffness coupling. So this is a coupling which is new for these laminates. Now let's see what else can we learn from these ABD matrices. So let's focus on these components A16 and A26. What do they do? They try to show the relation between your normal forces Nx and Ny with the shear strain gamma xy, or they show the coupling between the shear forces Nxy with the normal strains epsilon x and epsilon y. So these are called as shear extension coupling. So shear in the matter of either Nxy, they are coupling with the extensions epsilon x naught and epsilon y naught, or shear in terms of the strain gamma xy naught in terms of the extension forces Nx and Ny. So the B matrix we have already seen. This is the bending extension coupling. So where we are connecting the forces with the so we call it as bending extension coupling, because here we are connecting the bending is through the curvatures, we are connecting it with the shear forces N. And in this B matrix, this connects the bending in terms of the moments with the mid surface strains. And lastly, when we look at the D matrix, here too, this D16 and D26 have a special interpretation because they connect this bend and twist. So bending of mx and my is connected to this twist kxy, or these D16 and D26, they connect your bending of kx ky with the twist of mxy. So if you look closely, you will see that these ABD matrices bring in a lot of physics into it because they can show you which of these terms bring in different couplings. So here we have seen the shear extension coupling with the A16 and 26 terms, bending extension coupling using the B matrix, and the bend twist using these terms D16 and D26. Now, to give a better physical feel, now let's compare with other materials. So we'll see the deformed shape of a material, let's say when we apply a uniaxial load. We'll start with a simple isotropic material. Let's say this is the initial shape. Now let's see, because if you apply a uniaxial stress, how does this deform? As we know, since we are applying a tensile load, it stretches along the direction of the load, and perpendicular to the load it contracts. But here there is no shear deformation because that coupling is absent for isotropic materials. But let's say if we apply the same kind of loads to specially orthotropic material. So we have earlier defined what is an orthotropic material. We said that if our body or the coordinates chosen is in the directions of the principal directions. What are principal directions? Where we have these uh, unidirectional fibers. So these are aligned properly and then loaded. So now let's say if I am loading this in the along the fibers, how will this deform? So think about it and let's see how it deforms. So surprisingly, it will be no different from an isotropic material. So here too it will stretch in the direction of the loading and contract in the lateral direction, but here too there is no shear deformation. Why is it so? Because if you recall the Q matrix terms, the Q16 and the Q26 terms are 0, which means this coupling between the normal and shear is absent for a specially orthotropic material. But the same material, instead of applying along the direction of fibers, if I apply loads at an angle to the direction of fibers, then the deformation will be slightly different. There we will expect to see a shear. And why is it so? Because this is because now we have this extension shear coupling coming from these Q16 terms and Q26 bar terms. So this is for the generally orthotropic laminate, and let's say just for completion we will say this is a laminate with off-axis fibers. So here we are saying it has, in addition to the extension and normal strains along the directions x and y, it also has the shear strain. So let's summarize what are the number of elastic constants we need for each of these materials. So for isotropic materials, we know that we need two independent elastic constants. But for a specially orthotropic material, especially if we are looking at plane stress, we have shown that we only need four independent material properties. What are they? E1, E2, Poisson ratio, and the shear modulus. For the generally orthotropic material as well, things won't change. You will still have the 4 as the independent elastic constants. which are again the E1, E2 Poisson ratio and G12 the shear modulus. The reason why I'm trying to give you this summary is, now with this information, let's think how will a laminate deform under uniaxial loads. So let's say now we have a laminate, and let's say this is a laminate and we are applying a uniaxial load. So what do we expect? So since we have already looked at generally orthotropic, now we can expect that in addition to the normal strains, which is strain along the loading direction and in the lateral direction, it will also have shear. But that's not the only thing we see. In addition to all these, we also see a twist happening in the laminate, meaning in addition to the normal strains and the shear strains, there is also a twist, meaning even though we are applying an extension load, it twists. So it's hard to show it here, but it will be something like this. Okay. But the question is, how many independent elastic constants do we have in a laminate? It all depends on what are the layers we are choosing for this laminate. But let's say, for example, all laminas are made from the same material. So for each material, for each layer, we will have 4 independent constants. But if all layers, all lamina are same material, then again we'll have only 4 independent constants, which are again these E1, E2, Poisson ratio and the shear modulus. But of course there is no guarantee or there is no restriction about these different materials for a laminate. So the more the materials, then the more will be the independent elastic constants. But let's look it in a different fashion. If you look directly at the stiffness matrix, what are the components in the stiffness matrix? So for the laminate, we said we define the stiffness matrix using 3 different matrices, A, B and D. What is the size of these matrices? Each of them are 3 by 3. But in addition to this, is there any other information about this matrix, let's say A? For example, is it symmetric? The answer is yes. The reason why the matrix A is symmetric is because it is written in terms of the Q matrix, which again is symmetric. So which means all these ABD matrices are symmetric. And this symmetry is coming from the symmetry of this transform stiffness matrix Q. So if this is the case, how many terms do we have in each of these? So for the A matrix, if we consider the symmetry, we only need to consider 6 terms. And similarly for B matrix 6 terms and D matrix 6 terms. So in total, we have 18 terms which will define the stiffness of these laminate. So even though you have only 1 layer or 10 layers or 40 layers, all that information is captured using these 18 terms which define the stiffness of the laminate using the classical laminate theory. So let's summarize what we have discussed about the classical laminate theory. So we said we have shown it in 3 steps. In the first step, we showed what is the stress strain relation in a kth layer. In the second step, we showed the relation between the stress and strain in terms of this transform stiffness matrix and strains written in terms of mid-plane strains and curvatures. And lastly, we showed the relation between the force movement written in terms of the strain and curvature. For this, we have showed it can be written in these 3 matrices, which are now called the ABD matrices. So in this video, we have showed you the derivations of how we get to these ABD matrices. But there is actually a wealth of information one has to see in these ABD matrices, meaning there is lots of physical insight one can see once we look at a special cases. So in the coming videos, what we'll do is we'll look at special cases of laminate. Let's say there is a symmetric laminate. How does how do these ABD matrices look like? Or if we say if some of these layers are replaced from orthotropic to isotropic material, how do these ABD matrices change? Or there are some specific stacking sequences which are used in the industry, and there is a reason why these specific stacking sequences are popular, because they bring in some simplifications to these ABD matrices, which make them fabrication might be easier, or the analysis of those laminates will be easy. So we'll be looking all those in the videos from the next week. But in this video or in this week, we have summarized the classical laminate theory and showed the relations between the forces in terms of the strains, which can again be written in terms of the stresses. Okay then, thank you.